Hey, hello, and welcome to our webinar. We're going to be talking about neutron stars, black holes, and lots of other wonders of the universe. So my name is Katia. I'm a science writer, and I've got a degree in theoretical physics as well. And I travel the world to go to most amazing telescopes that are trying to uncover secrets of the universe. And I met some amazing people. So we're going to talk to you exactly about that, specifically about neutron stars, though. And joining me here today is Fernando. I met him on my travels in South Africa, in Cape Town. He's an astrophysicist, and maybe Fernando, you can say a few words about what you do.
Sure. Hi, Katia. Good to see you again. Good to not see everyone else, but I understand you're there. Good to join you tonight. So yeah, my name is Fernando. I was born in Portugal, and then I went to the US to study at university, and I got a PhD in physics at Princeton University. And that's where I started studying neutron stars, these very remarkable objects. And we use all sorts of telescopes to study neutron stars, or pulsars as well, as they're known sometimes. And I started studying them at the Arecibo telescope in Puerto Rico, which I believe Katia, might mention later on. And then essentially I spent most of my career at Columbia University in New York City doing a variety of research with pulsars, using telescopes around the world and around the Earth, X-ray telescopes outside the Earth's atmosphere, etc. But finally I came to South Africa about 4 years ago because of a remarkable telescope that was being built here by my South African colleagues that I believe Katia may also touch on later on. And that's when I met Katia when she came to South Africa, when we met and so on. And that was very good. So maybe, if I can ask you, Katia, we met obviously, but presumably you could have written a nice book on many types of astronomical objects, black holes, extrasolar planets, quasars. There's all sorts of interesting things out there. So why did you choose neutron stars?
Yeah, it's actually a bit of a funny story why I chose neutron stars. There was total serendipity. I wasn't planning on writing a book about anything at the time. In fact, as I said, I'm a science writer, so I was writing science articles. And at the time, I was writing a big story on neutron star merger for an American magazine called Quanta magazine. So what was happening actually, two neutron stars collided far away in space, and that was a big deal. And some of you might have actually even heard about it because it was covered quite widely in the media. So I was one of the journalists covering it. I remember I was actually at the 50th anniversary of Pulsar's conference in Jodrell Bank in the UK. And I didn't actually know it was happening just yet because I was there just to cover the conference. But I noticed researchers kind of talking in, weird hush hush tones, and they were like, something is clearly happening, and they're not telling me because I'm a reporter. I'm like, okay, what the hell? And then one guy, this astronomer from Australia, Matthew Bales, he was giving me a ride to my Airbnb. And he said, I'm going to tell you something, and it's probably going to be like the biggest story of your career, but it's not for sure that it's actually happening. So he was actually really careful. So he used a lot of like ifs and mights and whatever, but I knew that, he was telling me something and I better listen. So anyway, turned out, as I said, two objects far away bumped into each other and they produced gravitational waves. So here is a kind of, representation. We can't feel these waves at all. And the objects that produce them, they're actually really small. So neutron stars, I didn't know much about them at the time, but as I started researching, I found out that they're actually about 20 kilometers across and they're really, really dense. Okay, so, imagine if you take a city, the size of, I don't know, Manchester or something in the UK, and you curl it up into a ball, and you have two cities like that, and they are spinning around, and, each of them is spinning like crazy, maybe several hundred revolutions each second, okay? And then finally they collide. And when they collide, they disturb the fabric of space, disturb space-time so much that they send out these waves, just like when you throw a rock into a pond, okay? And it sends out ripples. And we managed to capture these ripples as they wash over the Earth. And that was the story I was writing. after what Matthew shared with me in a very, very hypothetical conversation. Anyway, after I did that, I suddenly received a LinkedIn message from a guy who claims to be a publisher at Harvard University Press. And he's like, well, I read your story and I read other stories you've written. Do you want to write a book? And first I ignored the message because I thought, LinkedIn, I usually get some weird marketing requests on LinkedIn. It's probably spam or something. Well, it turns out it wasn't spam. It was a real publisher and he really wanted me to write a book and he gave me complete carte blanche. He's like, you can write about anything. So I thought, okay, cool. I just written the story. I'll see if a lot has been written on neutron stars. And actually, that's not the case. A lot has been written on black holes. Everybody knows black holes. They're super, popular. Stephen Hawking and others have, done a really great job so that everybody knows them. But nobody knows pulsars or neutron stars so much. So I decided to write a book for anyone on neutron stars. And then to actually write about them better, I thought I would actually travel the world to different places where scientists are studying them. And
so that's very cool. So this event you're talking about, I presume this is this gravitational wave event that was detected on Earth on the 17th of August of 2017, which was just a few days or a couple of weeks before that conference you're talking about. I was at that conference as well, funnily enough. I don't recall meeting you there, but these are big conferences. So that was a remarkable event indeed, as these two neutron stars, as you said, the mass of the sun is jammed, is condensed into a ball the size of a city. So remarkably extreme objects. And that was one of most, I've been studying neutron stars for 30 years, and that was one of the most remarkable events in the neutron star world that I can think of. So yeah, that's indeed very cool. So what do you find, what else you find intriguing about these neutron stars? And I've already mentioned neutron stars or pulsars. I've used those names interchangeably. They're not quite the same thing necessarily. So yeah, can you tell us maybe a little more about what's the difference?
Yeah, exactly. So I've got a slide here. I hope people can see. So it kind of shows you very roughly how neutron stars are born. So basically, as you said, Fernando, it's it's a really, really dense object. So it's a mass of the sun, or more condensed into a small ball. So indeed, if you look at our sun, the sun is really, really heavy. And if you take all that mass and you put it into a tiny ball, you get a neutron star. So the way it's born is basically when the sun is going to die, it's going to be a really boring death. It's just, gonna, turn first into, as you can see here, into a red giant. And then it's just going to turn into a white dwarf, and it's just going to stay there forever. And, whatever, doesn't matter. Really boring stuff. When a big star dies, a big star, from 8 times and more the size of the sun, the mass of the sun, it's not going to be boring at all, because it's going to go boom, it's going to go supernova. And out of that supernova explosion that we can actually see with our optical telescopes, what will stay behind is this teeny tiny object, only 20 kilometers across or so, and that's the neutron star. So it's going to spin like crazy, and it's also going to emit radiation. And so that's the question about pulsars or neutron stars. So if we can detect this radiation, and it's kind of spits out these jets of radiation from both poles, and it's spinning in space. So if you imagine, like, somebody standing there with a flashlight and is going, the person is spinning the flashlight around, you can only see the flashlight if it goes, into your field of view, right? And then you will notice that there's a flashlight. Same with a lighthouse in the sea. So it's constantly spinning, but ships will only see it if they are in the field of vision of that, of the spinning lighthouse. So that's what happens with pulsars, with these neutron stars that are emitting radiation. We can only register that radiation if the Earth and the telescope happens to be in the field of vision of the radiating pulsar. And so that's why we get pulses. So that's why they're called pulsars, because we only get pulses like beep, 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 and so on as it's spinning in space. And sometimes we don't register those, the radiation at all, but the neutron star is still there. So there are different types of neutron stars too. But what's amazing about them is that they are, as I said, they're so dense. And when those two neutron stars collided, they actually turned into a black hole. And maybe some people actually watched the Nobel Prize presentation this year. Nobel Prize in Physics was given for black hole research, which is really, really cool. And people may not realize that black holes, yeah, they are like really dense too, but that's not matter anymore. The densest form of matter that we know of are neutron stars. So you just add a little bit more matter to them and they will collapse into a black hole, or you like bump two of them together, they will also collapse into a black hole. So I find it fascinating.
Yeah, so this is a nice diagram of the simplified life cycle of, well, stars, and how you get neutron stars in some cases, or pulsars. But of course, our friends watching this from their homes maybe tonight, they should know that what you see here on this slide is either an artist's impression, or in some cases, some images of the sky taken with telescopes like the Hubble Space Telescope. And I must say, as a guy studying pulsars for 30 years, where you do not take pictures of pulsars per se, because of course pulsars are 10 kilometers across and they are thousands of light years away, so they're essentially a point. So it's never sort of visually very appealing, which our friends that use the Hubble Space Telescope and so on, they have that going for them. So I was curious, like, how do you, I mean, obviously you have a PhD in theoretical physics and so on, but how do you make this particular topic accessible to a general audience?
Yeah, well, as we just discussed, all these visuals, it's so cool. Like when you say something like, you just take all this mass from the sun and you put it inside a teeny tiny ball of like 10 or 20 kilometers across, and people just, they can visualize it suddenly. Another comparison I used in the book is, for instance, if you like pretend you're a child, right? And you take you decide to steal some dough from the cake that your mom just baked, okay? And if this dough is made of neutron star matter, well, just what's on your finger is going to pull you down with like millions of tons. That's how heavy it is. It's a remarkably heavy matter. And there's so much that we still don't know about them. Or another visual representation of the lighthouses, that's also, I think, very exciting. But most of all, what I found fascinating is not the science itself so much. I mean, science is really cool, obviously, but if I just write it like that, it's going to be a very sciencey book or presentation or whatever, and it's not going to be interesting maybe to a wide audience. What I find super cool is the people behind the science, because there's no science without people, and people like you, Fernando, and lots of other really cool scientists I met on my travels, who get super excited when they talk about about these objects, just like you get excited, Fernando, like now, even when you look at this diagram and you want to tell people like how it works, right? So people know how much it matters to you. So some people, they spend years, even if they, I describe a couple of people who bumped into mistakes, and then they had to acknowledge their mistakes, but they just still keep going forward, and they spend their entire careers on these secrets that the universe is still kind of hiding from us, and we're unlocking one by one. And I just find it super cool talking to all those people, and men and women of all ages. I met young postdocs and PhD students who are already making remarkable research, and it's just really cool.
So you traveled, obviously. I mean, remember, that's how we met here in South Africa. And presumably you traveled, well, I know you traveled in many places around the world, including to telescopes where I've never been myself professionally. So I'm a little jealous. But so yeah, as you traveled, I mean, you knew something about neutron stars, I suppose, but presumably you needed to learn more. And so what helped you to get on top of the neutron star science as relevant for your book?
Yeah, well, what happened is just doing a lot of research, analogies helped as well, asking a lot of questions whenever I would interview someone. And of course, that was kind of the time roughly when I also got my degree in theoretical physics, and I specialized in not in neutron stars per se, but my thesis was on dark matter actually. So that was also pretty cool, because one of the chapters of the book actually talks about dark matter. So that's kind of fascinating.
Cool. Do you have maybe some slides of your travels or something? I don't know if you have any to
Yeah, well, let's see. So here is just a presentation of a pulsar so that people can kind of see what it looks like. It's just this object with radiation coming out of the two poles. This is a neutron star, and as I said, there's still a lot of mysteries about them. For example, we don't know what's inside, and actually at the very center of neutron star could be like some really weird forms of matter. So we are still trying to understand it. There are several instruments on Earth that are trying to recreate it. But to your point, where I've been to find all of this out, just a few slides here, like this is, for example, a really cool telescope in Australia. So I arrived to Melbourne, and then, so I was actually quite lucky because I worked as a journalist at the time. It was my idea to travel the world for the book, but no publisher will finance your travels like ever. So it was like all on me. And I thought, okay, how am I going to pull it off? Do I have to like do a Kickstarter or something and, finance my travels? But at the time I was working for Wired magazine. And of course, I covered a lot of science and technology as well. So this particular instance, to go to Australia, I was invited to a technology conference in Melbourne. And they paid my flight. So that was really cool. And I presented at the conference. I did a panel. And I also, on top of that, wrote a few stories for Wired, independently of the conference. But when I was there, Matthew Bales, whom I met in Jojo Bank, drove me from Melbourne to this amazing place. In Australia, they call it the Dish. And they actually love it very much. All Australians know, and they're very proud of their dish. And I met, there are not a few people, there are just a few people there now. Astronomers used to actually live there at the time. And the guy I met there, John Sarkisian, he's been there for years. He's very nostalgic about, how astronomers don't come to the telescope anymore. They do it remotely. So I didn't meet a lot of people there in person. But what I did do, actually, he gave me a ride in that humongous dish. Okay, so we actually stepped inside, and there was another guy in the control tower, and he tilted it upwards. And so you're standing in this giant soup bowl nearly, and you suddenly see the tree line disappear. And it's such an amazing feeling. Like I've never felt anything like that before. It was absolutely unbelievable. So that was one of the things. And
yeah. If I may just interrupt you there,
yeah.
just because this is very personal for me. This is the Parkes telescope, 64 meters across there, the diameter, 2/3 of a football field in size. And I've spent months of my life in that dish, and jogging up and down between there and 1 kilometer away, which is the quarters for us observers, so we might sleep and eat and then spend the whole night or the whole day, because of course radio waves propagate during the day as well. In that structure, very, very beautiful telescope. And for again, our friends who are listening tonight, just out of interest, if you're old enough to have watched the moon landings, Neil Armstrong walking on the moon in 1969, the TV signals that people saw on their TVs that night were transmitted from the moon to this dish and then elsewhere around the world. So this dish, as well as many other radio dishes, have had a long life, a variety of occupations, and certainly this one, the Neutron Stars.
It's also tracking the Voyager twins, right? So 2 Voyager spacecraft. Parkes is helping track in interstellar space right now, which I find also unbelievable. When I was there, they showed me the Voyager 2 on the screen, and John was like, look here, this dot is the Voyager spacecraft that you're looking at in real time. I was like, oh my God. So that was...
Yeah, that's very, very cool. Yeah. Okay, so that one I've seen. Show me more. What else have you, where else have you been?
So these 2 guys, as I said, the book is very much about people. So it's Dick Manchester and Ron Eckers. So I met them in Sydney. It's still Australia. I got a flight from Parkes to Sydney, and I did a presentation about the book, upcoming book at the time here. And I interviewed a lot of really cool scientists. And Dick Manchester, actually, he did something unbelievable. He uncovered the first glitch of a pulsar back decades ago. So I do talk about glitches in the book quite a bit. And this is something that happens when the rotation suddenly changes. So we can actually time pulsars, and we know, the regularity, most of them rotate pretty regularly. But sometimes they don't. They just, misbehave. And when he noticed it, he thought it was like maybe something wrong with the telescope or whatever, but it wasn't. It was actually the pulsar that he was observing that was being weird. So that was like it was a really cool story. And these glitches, they also helping us to understand what's inside neutron stars, which we still don't know. It's a huge, huge mystery. This is just another of my travels, and Fernando, you probably, of course, recognize the people and the room. This is Cape Town, control room, and they are looking at images of this amazing array, which is called Meerkat, which I found really, really cute. So it's about, it took us about 8 hours to drive there from Cape Town. So it's an array of radio dishes, and it's a precursor to a much bigger telescope, radio telescope, which is called Square Kilometer Array. And once it's built, it's going to be really, really sensitive. And this guy is already quite sensitive. I'm sure, Fernando, you can tell people more about it because it's so probably dear to your heart, right?
Yeah, just a little bit. I mean, for people, so you've already seen two types of radio telescopes in the images that Katya's shown you. The Parkes telescope is what we call a single dish. So as you saw, it's a big dish. I mean, 64 meters in diameter. This one here is made up of 64, as it happens, that's a coincidence, 64 separate dishes, each of which is about 13 meters in diameter. So this is still tall structures. I mean, each of these dishes is about 5 stories high or so. But now you have 64 of them spread out over a diameter of 8 kilometers in this case. So I won't go into the details, but effectively this enables you to make much more detailed images of the sky, to actually get kind of pretty images of certain parts of the sky. And as Katya said, this is a South African project, fully South African funded, developed, which is amazing. That's another story, another tangent. Following the end of apartheid, the government here in South Africa decided what, amongst other things, of course, what could they do in science that would put South Africa on the map in a sense? What was their comparative advantage? What could they actually be world class at in terms of some science? And astronomy was one of the things that came out of their white papers and studies and so on. This was back, in 1995 or so. And then in the past 15, 20 years, really, my colleagues decided to get involved with this international endeavor of the International Square Kilometer Array Telescope, which now has about 10 nations in it, a handful in Europe and North America, China, India, Australia, South Africa. And since there was no real history of radio astronomy in South Africa, they decided to build this telescope. And this is not a toy. This is not a prototype. I mean, it's much smaller than the eventual international project. But this telescope right now, it was inaugurated 2 years ago, and it is the best in the world for some things, for some investigations. So yeah, this is a very remarkable telescope. But again, I would like to point out it's the story of the people behind it. I mean, my South African colleagues who built this very interesting instrument. Cool, very cool.
Absolutely, thanks. Exactly. This is just a picture of, on my way there, amazing landscape in Northern Cape. If some of you guys have traveled across South Africa, you probably recognize it, but it was unbelievable. This is a completely different place now. Now we are in Europe. So I do talk, as I mentioned before, I do talk about dark matter in the book, actually. And this is a dark matter detector under the Gran Sasso mountain range in Italy. It's really cool. So basically it's a huge tank full of gas called xenon, and they're trying to catch particles of dark matter that are like coming through the atmosphere. They haven't caught anything yet. Actually, they've been looking for dark matter for decades. The first guy who suggested that there could be something like that, some dark matter in the universe, that was back in the 1930s. Franz Zwicky. Actually, my book is dedicated to him. I find him an absolutely fascinating character. Not an easy character, from what many people told me. Ron Eckers in Australia actually worked with him, which is crazy. Back in the 70s, I think. So he knew him firsthand. Anyway, the story of dark matter is pretty cool, and we'll come back to it maybe later because I have another slide. But this particular...
But sorry to interrupt. Yeah, so this is very cool. I've never been to Gran Sasso, very jealous again. But obviously dark matter, we don't know what it is, but one thing it does have is gravity. That much we know. It affects other bodies that have mass. And neutron stars, as we've already discussed, they're very dense. They have very powerful gravitational forces. But so what's the connection here? I mean, why did you go off on a tangent to dark matter when you were studying pulsars?
The connection is that there's a chapter in my book that talks about a weird signal that that was noticed a few years back coming from our galactic center. And some people said that it could have been from dark matter. And other people said, no, it's probably from a population of so far invisible pulsars, maybe like hundreds or even 1,000 of them in the galactic center, because signals could be very similar. And we still don't know what it is. There are papers that come out every now and then that kind of swing the balance towards dark matter or pulsars. And, future telescopes or current telescopes that are currently being upgraded, like the one in West Virginia, GBT or even SKA in the future might actually help us see if there are indeed pulsars in the galactic center or not, or if it is dark matter. And so I just wanted to see firsthand how they're looking for dark matter. They're also trying to recreate it in certain experiments. There are various ways, and there are also different types of hypothetical dark matter particles, of course, so there are different experiments looking for different things. This particular one is looking for heavier particles of dark matter, but as I said, so far, sadly, we haven't found any evidence, any direct evidence of dark matter, so to speak.
Okay.
Oh, and now we're somewhere completely different. So this is a fantastic telescope with quite a sad history over the last few years, unfortunately, and really cool history if you go a little bit further back. It's called Arecibo, and it's in the middle of a rainforest in Puerto Rico. Amazing nature as well. It was built in a sinkhole, as Fernando mentioned before. There are lots of different designs of radio telescopes, and this one, so the dish doesn't move, it's just in the ground, it's completely static. What moves is the dome that you can see on top. And so what might be interesting for those of you who are not into astronomy necessarily, you may have actually seen this telescope in the movies, because it featured twice, I believe, at least, in the movie Contact with Jodie Foster. She was like sitting there listening to aliens. And she was actually sitting literally in one of the huts here on site. The other movie was The Golden Eye with, what's his name, Pierce Brosnan. And funny story, as you can see, there's the suspension bridge on top. And that's the bridge people take just to go to the platform, to the observation platform. And I walked on that bridge. And I was told that apparently Pierce Brosnan, when he was filming here, he has height anxiety. So he couldn't walk on that bridge, okay? So I was like, this is super cool. I'm doing something James Bond couldn't do. So there was like a personal moment for me. But, that aside, Arecibo discovered a lot of pulsars. It's done a lot of really fascinating work in radio astronomy. Sadly, it's been battered by a hurricane a few years ago, and then they were repairing it. And in the middle of the repairs, a cable snapped in August, and then another cable snapped just a couple of days ago. So they're still kind of deciding what to do, like how the whole platform could now collapse. So yeah, it's an amazing instrument, but I don't know what's going to happen to it.
Maybe just to give a sense of scale to our friends tonight here who are joining us. So that dish is 300 meters across, so 3 football fields. That catwalk or walkway where you were, Katia, is about 150 meters above the dish. And that suspended structure there weighs 900 tons. So maybe that gives you a sense of the vastness of the scale buried there in the midst of the rainforest. So yeah, it's quite an interesting. So just from a civil engineering perspective, it's a remarkable instrument.
Yeah, absolutely. It's and another actually really cool thing, and I have a whole chapter just on that. This particular telescope discovered the very first planet around a pulsar. And there's a bit of a sad story with that as well. I mentioned in the beginning that some scientists had to deal with disappointments, just like in any career, I guess. Well, what happened was there was another group in the UK who thought that they found a planet around a pulsar. So if you think about it, a pulsar is a dead star, okay? So the star goes boom, there is this core that's left behind, that's spinning like crazy. So that's why actually the title of my book, you know, I say the quest to understand the zombies of the cosmos. So they're indeed zombie stars. They're not alive anymore, but they behave as if they were. So anyway, around the zombie star was magnetic fields and this radiation, you know, radiation jets coming out, and they found a planet. So according to their calculations, they announced it to the world. The astronomer Andrew Lyne, he was super happy, and they published it in Nature, which is this prestigious academic journal in Britain. And then they were supposed to announce it at a big conference in the US, this annual astronomy conference in January. And there was this other guy in Arecibo who also found a planet. And he knew about the first, you know, the other group that found the planet, another planet first. So he was like, okay, well, I found a planet, really cool. I'm going to announce it too. But, you know, I know that I'm not going to be the first one. So whatever, nobody's going to pay any attention to me. So this guy, Alex, he's, you know, getting on a plane. He's coming to the US to present his planet as well to this at this conference. He arrives, and a couple of days before, the organizer pulls him aside and he's like, you know what, actually, the other group, they just retracted their paper because they didn't actually find the planet. There was a mistake in their calculations, and they're gonna admit it publicly today. So actually, you're the discoverer, you're the person who discovered the planet. And so this guy, Alex, he's like, oh my God, this is amazing, of course, but also awkward. So he had a chat with Andrew. Andrew, of course, was very sad already. So he knew what was going to happen, that he had to kind of get up and publicly say to the world that, you know, he didn't find the planet. And that's exactly what happened. So he went up on stage, and there were lots of journalists in the room, and the journalists they all had the preliminary program. They all knew that a planet was going to be announced. So they're ready to write their stories. He goes up on stage and he's like, you know what, actually, I didn't find a planet. So they're like, oh my God, they rush out of the room to file their stories that there is no planet. And Alex goes up on stage and he's like, well, actually, there is a planet, but I found it with a completely different telescope. So they all rushed back into the room and they filed their stories again. There was a huge media frenzy. Everybody was going completely crazy. But, you know, it's a little bit of a sad, touchy story. And I spoke to Andrew. He's still a little bit sad about it, of course, understandably so. But I find it fascinating, you know, all the courage that it must have taken him and his collaborators like Matthew Bale, so actually also one of them, to get up and just say that, you know, admit the mistake, but just like that in front of everyone. So that was, yeah, that was really, anyway. And Alex, he found his planet with this guy, with this telescope. So that was really cool.
Yeah, that was 1992. That's right. Cool. You have other images of other telescopes, or
yes? So now we go to Italy again. Actually, Gran Sasso was also in Italy. Anyway, but this is a completely different detector. So this is Virgo, and it detects gravitational waves. We can see only one arm. It's made of two arms that are connected at a perpendicular angle, and they can detect these tiny disturbances from far away, you know, cataclysms like mergers of neutron stars, for example. And when I was there, I was even told, when I was in the control room, not in the control room, but in the room where they actually, where they have all the sensors, to walk very quietly because it even registers footsteps. So it was quite fascinating. This is Canada. So this telescope, again, a completely different design. It's called Chime, and it's a really cool detector of FRBs, fast radio bursts. This is a sort of unfinished chapter, so to speak, in the book, in a much bigger book about neutron stars, because we don't know what they are. We think we know. We are pretty sure that we know actually that they must be young magnetars, but we are not 100% sure yet. These radio flashes, they are very, very brief, quite far away, not in our galaxy, although one was registered in our galaxy just recently, which is really cool. But usually they are extragalactic. And this telescope and a few others around the world, one in Australia is also pretty cool, is catching these FRBs, you know, a lot of them every day, I believe now. So which is really awesome. And by the way,
Yeah.
this particular guy is located in a wine country of Canada. So they have amazing, amazing wines in British Columbia. You have to get there on some really small plane, propeller plane from Vancouver, and which I completely didn't expect that in Canada, it's called Okanagan Valley, and you can buy unbelievably great wine. So if anybody ever travels there, don't forget to drink the wine as well. So yeah, that's it. That kind of concludes my slides on the travels. But I've been to
Very,
other places too.
yeah. Now it's funny. You just mentioned FRBs, fast radio bursts, and you said we don't quite yet know what they are. This is true. Obviously, there's great interest in them because we know they come, well, most of the ones detected so far from well outside the galaxy. By the way, someone is confirming that the wine is great in this region of Canada. I'm just looking at the chat window here. So very good. It must be true. What you just said. So right. So FRBs, we really don't know what they are. Most of the ones detected, with the possible exception of the one you just mentioned, are from well outside our galaxy, far, far, far away, hundreds of millions of light years, etc., far away. But of course, then, so that they're a remarkable probe, we hope, they're like a very bright flashlight far, which then illuminates space between its origin and us. So it's a new tool with which to learn about the universe. So that's fantastic. But of course, we'd also really like to understand what are they, what's powering them, what's the engine, and so on. And one of the, I think you mentioned already, well, I don't know if you mentioned, but magnetars, I just wanted to mention, I mean, I think you mentioned magnetic fields and pulsars. Pulsars have super strong magnetic fields. Those of you who are still used to walking in the woods with an old style compass, that works on the basis of the fact that the Earth has a magnetic field, right? But its strength is about 1 Gauss in those units, 1. Well, a normal neutron star has a magnetic field that's 10 to the 12 times larger than that. So 1,000 billion times stronger than the magnetic field of the Earth. So those are the normal pulsars. But then magnetars, which some people now think may actually be the cause of these FRBs in very distant galaxies, those are even stronger, have even stronger magnetic fields by a factor of another 1,000 or so. So I mean, to me, always describing the gravity of a pulsar, the size, the sun's mass compressed into a ball the size of the Earth, spinning up to hundreds of times per second. That all sounds absurd enough, like a kitchen blender, except it's the size of a city, has the mass of the sun. Sounds absurd, but at least I can picture it. But the magnetic fields, to talk about a magnetic field of 10 to the 15 Gauss, I mean, what the heck does that mean? And how, I'm curious, in your book, which I haven't read yet, I will when you send me a copy, how do you, for a non-astronomer, how do you talk about these strong magnetic fields? Or how can people grasp, like, in your opinion?
Yeah, well, I think comparisons that you had we could compare them to magnets we all use, like a fridge magnet or something. It's completely incomparable in strength. They are the most magnetic objects we know of. But, again, when I talk about magnetars, I talk a lot about the people who discovered them. And that actually goes back to the 1970s. There was a PhD student, and she noticed, weird, well, not like lots of people noticed. So basically, they registered weird flashes of light, of radiation, and everybody was like, okay, these are gamma ray flashes. And they were kind of not very well known phenomenon at the time, but people were already talking about them quite a bit. But she disagreed, and she was just a PhD student. She was like, no, I've worked on gamma ray flashes before. That doesn't look like that at all. It's something completely different. And then it took her about 15 years or so to wait for the technology to mature. And she was working at NASA at the time already, when she was able to place an instrument on a satellite that they were launching for something completely different. And that particular instrument then registered those signals again, and they were completely different from gamma ray flashes, and that's why she then together with some really important theory brought forward by two completely different people, two theoreticians. They put together this model that, it could be neutron stars that are extremely, extremely magnetic. So they're still neutron stars, but they're just way more magnetic than regular pulsars. And this is what I find fascinating, like how it was actually discovered, how many years it took for one person. Well, it was not just her, of course, and she participated in a lot of conferences, but still, it took her years to actually find out more about magnetars. And you yourself, Fernando, you work a lot on magnetars too, right? And I remember when we chatted, you told me about those really cool magnetars that kind of fall asleep and then you can't see them anymore and then they revive. And you had like an example of a couple that kind of died and you thought that they died forever. And then suddenly, like a few years later, they're making, giving out signals again. And yeah, and just to observe an object for years, I mean, that takes a lot of patience. And yeah, I find it's really
Yeah,
cool.
that was actually kind of a cool story. Yeah, if I and maybe I saw already your next slide, which maybe I can connect it to this discussion on magnetars in a way.
Oh, this one here.
Well, no, the previous one, the Galactic Center. Yeah. So do you want to explain what this is here, what we're looking at?
Yeah, well, this is what was taken with Meerkat Telescope in South Africa, and this is actually a really cool picture of our own Galactic Center. So yeah, I'll let you take it from
Yeah.
here.
Okay. So the Meerkat Telescope, as I mentioned, it was inaugurated in 2018. So and that's when this image was made, which is the clearest view we have in radio waves of the center of our galaxy. That super bright area there, kind of center right in the image, is where this massive black hole at the center of our galaxy resides. It has a mass of about 4 million times the mass of our own sun. Matter falls into it, etc. All sorts of bizarre things happen in this region. And so, but we can't observe it with an ordinary telescope, a normal optical telescope, because there's too much dust between us and the center of the galaxy, which is about 25,000 light years away. So all the normal light gets absorbed, but radio waves propagate through that dust. So if you have the right telescope on Earth, you can make an image like this. And there's a lot of funky things here, these filaments sort of vertically aligned, narrow filaments. Nobody really knows exactly what they are, except they probably have to do with magnetic fields. When you don't know what you're talking about in astrophysics, you always say magnetic fields, and they'll solve your problem if you know how to interpret it. Anyway, back, connecting to the magnetars. So as Katja said, so the funny story there is the woman that she mentioned that essentially originally discovered magnetars, although she didn't know exactly what they were, was Krista Covelliotto in the US. And these magnetars were all discovered and studied with X-ray telescopes, actually in space, X-ray and gamma ray telescopes, but not radio telescopes, because magnetars did not appear to emit radio waves. So much so that papers were written by theoretical physicists explaining why you couldn't detect radio emission from magnetars, because they had very strong magnetic fields, and then these quantum electrodynamic effects, funky effects, that where a photon splits into two photons instead of an electron and a positron, all sorts of things. That was the reason why you could not detect radio waves from a magnetar. But then in 2006, using that Parkes telescope that we saw before in Australia, I happened to detect radio emission from a magnetar, and it was absurdly bright. So bright that we were very confused. At first, I thought this was some sort of earthbound interference or from a satellite or something, because it was ridiculously bright. It was the brightest pulsar I think I've ever discovered. And but then eventually we realized, no, it's from space. It's from that magnetar. But we realized that magnetar was going on and off. Every few years, kind of, it would lie low, and then once in a while it would burst up and be very active. And so that was 2006. To connect it to the stories that Katia mentioned earlier about the discovery of planets, I remember we wrote this paper in Nature, in this journal. But that week, unfortunately for me and for the press team at my university in New York, that was the week that in Europe somewhere, the International Astronomy Union decided to downgrade Pluto from a planet to a dwarf planet. That was back in 2006. So that was much bigger news in the astronomical world, apparently, or to the general public, than my puny discovery of radio waves from magnetars. But still, it was very cool. And then there's still only about 4 or 5 of these magnetars known to emit radio waves. It's quite rare. They're all in our galaxy, except perhaps those fast radio bursts, if they are magnetars. hundreds of millions of light years away. That's a different story, although it may be linked. Anyway, but just to connect it to this beautiful image of the center of our galaxy taken with the Meerkat Telescope, back in, so this is, let me think, this is 2016, I think, that's right, where we didn't have the full 64 dishes to make this image. That's the full Meerkat, 64 dishes. But we had about a quarter of them, 16 dishes. And I happened to fly to, I was flying to Australia to go to that Parkes telescope fundamentally, to do other observations, when my colleague in Australia, John Sarkisian, that Katia already mentioned, he emailed me as I was at the airport and said, hey, that magnetar is again active after years dormant. And I was like, wow, awesome. Please start observing it every chance you get. And then he told me, we can't, because the telescope is going down for a maintenance period. We have to do a lot of electrical work for the next month. And I thought, oh my God, disaster. Like, you know, it's just turned on. It's super important, super interesting anyway. And we can't observe it. Now, this is in the southern hemisphere. And we have mentioned this, but there are, for maybe obvious reasons, historically, there are more radio telescopes in the northern hemisphere than the southern hemisphere, although that's changing. And so I remember on the plane on the way to Australia being a bit bummed and thinking, ah, Jesus, this thing happened and now we're not going to be able to follow it up. And then I realized, wow, there is this telescope in South Africa. I'm the chief scientist of that telescope. It's still being built, but actually maybe we can use it to follow up the revival of this magnetar. And that's what we did. So actually there's that little connection with Meerkat. And then we wrote the very first paper using this new Meerkat telescope was on one of these magnetars that once in a while emits radio waves. And so it's quite interesting how all of that I think is very connected. So that's this beautiful picture. Now the next one you had, sorry, which you showed.
This is the last slide I have, yeah, and just kind of shows the difference between different neutron stars.
Yeah. And so maybe just, I mean, one that you don't mention it here because we don't know exactly, again, going back to these fast radio bursts, which really, so the first one of those was discovered in 2007, again, at the Parkes telescope in Australia. It's been a remarkably productive instrument. And one of the reasons, by the way, is because it had half the sky for itself for many decades. It was the major pulsar telescope in the southern hemisphere. But so yeah, nowadays, since 2007, we're starting to know a lot more about fast radio bursts, FRBs. But what specifically have you discovered? Have you discovered anything, or do you mention anything about them in your book?
Yeah, I have a whole chapter on FRBs actually, so I'll stop sharing the screen now because there are no more slides anyway. Yeah, I've got a lot of I've got a chapter on FRBs, which talks about the whole history of it. And there is an interesting twist to it. So people who, again, who are not astronomers, they might kind of find intriguing that quite a few people also think that FRBs might be aliens. Well, not so much anymore now, but in the early days when they were just discovered, because first we found just one and then we couldn't find anything else for quite a few years. To the point that one Russian oligarch actually gave quite a bit of money. I can't remember how much, what is it, $100 million or something? It was like the biggest private investment, I think, in radio astronomy like ever. It was the money. They upgraded Parkes, they upgraded Green Bank Telescope, I think, and a few others. And, and they are kind of looking for SETI, but they're also, the money actually went to a good cause as well in terms of observing FRBs. So that's quite an interesting twist.
Yes, that's right. So you're speaking of Yuri Milner, I think.
Exactly, a Russian
investor, Russian investor that lives in the US. And yeah, as you said, he decided to spend $100 million of his own money, contributing it over a decade or so towards this quest of seeking for extraterrestrial intelligence, the search for extraterrestrial intelligence, SETI. And as you said, for technical reasons, radio waves are a very good, well, we think, we don't know how SETI thinks after all, or if they exist, but we think it might be the way to do searches for communication, if you will, from extraterrestrials on other planets around other suns. And so therefore they're naturally interested in these large radio telescopes like Parkes, like GBT in the US. And in fact, like Meerkat, in fact, just today I had a meeting that we don't yet have that capability to search for extraterrestrial intelligence with the Meerkat Telescope, but sometime next year, I think that will happen, as a result of the investment by that man and then our colleagues at University of California, Berkeley, and so on, who are doing the technical work. So that's very interesting technical work. And we get to learn a lot, as you might expect, though. So far, they haven't detected any aliens anywhere in any of these telescopes, or you would have read about it in the newspaper. But what we do detect a lot is intelligent life, but it's all from our own planet. Because this is one thing that we haven't talked about, but maybe some of our friends tonight might be interested. Sometimes people ask me, so like, what's the best place in the world to do radio astronomy, this and that. And I always say, well, in our solar system, the best place to do radio astronomy would be on the backside of the moon, the far side of the moon that we don't generally see. And the reason is that I don't have my cell phone with me, but you all do. I have a laptop, and everything that humans, well, a lot of what humans do, modern civilization, produces radio waves. And, we spend all this time and money and effort building a telescope in the middle of the semi-arid region of the Karoo in South Africa. 64 dishes, 8 kilometers across. And to give you a sense of scale, if one of you flew out to Jupiter and carried your cell phone with you, obviously you wouldn't be able to communicate with anyone on Earth, no service, no signal, but we could detect your phone. We could use Meerkat to detect your phone very easily. And so there is all this interference, as we call it, radio frequency interference, that essentially modern civilization makes, which makes our life really hard when you're trying to detect faint signals from halfway across the universe. And so when our colleagues try to detect extraterrestrials, what they end up detecting is, satellite signals and cell phone towers and whatnot. If you went to the backside of the moon, then the whole moon would protect those telescopes from the Earth's emissions, and that'd be fantastic. But that's another story. So in any case, so aliens, so far not yet, but soon maybe Meerkat as well will be in that game. So anyway, Katia, I was wondering, well, you've written this book. I want to get a copy. I want to read it. But are you writing about anything else? Anything?
Well, not. I kind of switched careers. Well, I'm still a science writer, but right now I work at IBM Research, so I'm writing about quantum computing and AI, not so much about astronomy anymore. But it doesn't mean I'm not going to write another book on astronomy and astrophysics. So that's a lot to explore, of course, in the universe. But I actually see that we only have 8 minutes left, and we've got 2 questions here in the Q&A. So I don't know if any other people gonna type anything else in the last few minutes, but maybe we could address these 2, Fernando. So I don't know, how does it work?
Okay.
I don't know if people can see, but basically this person is asking whether all neutron stars spin rapidly and why. Well, I'm sure, Fernando, you probably can give a lot more details on that. But when I was writing the book, I found it actually really fascinating that not all of them spin at the same rate. That is true. Some of them are really, really slow. And what was actually really cool, the slowest pulsar ever was discovered by a telescope, which is called LOFAR. And it doesn't look like a telescope at all. Okay, it looks like a bunch of solar panels that like fell flat in a swamp. And when I went there, it's in the Netherlands. You literally drive in the countryside for about like 2 hours from the train station, and then you have to walk. It's a nature reserve, so you walk in the swamp, you get your feet wet, you have geese flying all over you, and and you see these weird flat solar panel like things, and also a bunch of antennas that look like literally like Christmas tree antenna type thing. And this is a telescope that also detects pulsars, and it spotted a few years ago the slowest pulsar ever. And the guy who found it, I think he was at the time either a PhD or a postdoc, and he was back home in Malaysia when he found out that his pulsar was the slowest ever. And he shared the news with his family in Malaysia, and they were like, yeah, so what? And he was so upset that they couldn't, participate in his enthusiasm, and he couldn't wait to get back to Manchester to share it with his colleagues. So his like star moment was when he was with his family, who just didn't get it, unfortunately. So anyway, but there are also pulsars that spin really, really fast, and we call them millisecond pulsars. They're very, very old. And what's really cool about those pulsars, I personally call them like zombie squared, because they're like, you know, radio pulsars that were spinning like a normal radio pulsar, but happen to have maybe a companion, like another star next to it. And so this radio pulsar, it's spinning, spinning, spinning. It starts, you know, gobbling up the matter from the companion star, and it's like eating this matter. It's spinning faster and faster and faster, and then it turns into a millisecond pulsar, which is very, very old, and we call them recycled pulsars as well. And at that time, we can't spot them in radio anymore, but in X-rays. Anyway, so those pulsars are incredibly fast. So it's completely different from regular pulsars, right? And if you want to jump in, Fernando.
Yeah. So I think Katja has addressed the question that was posed by Evan L. Last name, but he was asking, do all neutron stars spin rapidly, or is it just the pulsars that do? And I mean, in a sense, this is a matter of nomenclature. As Evan correctly points out, surmises, I mean, every star rotates, you know, our sun rotates, you know, roughly like once a month on its axis. I mean, it's a ball of gas, but still, you know, you can follow features on its surface, etc. And then if you imagine that just collapsing to the size of a city, it would maintain what we call the angular momentum. And that's that old analogy of a dancer, ice rink skater, you know, arms out, spinning, brings the arms in, spins much faster. That's what we call conservation of angular momentum. So at some very, very, well, simple level, that is what's happening. That's what causes a young neutron star just after it's born to spin. Then they slow down, and then there are the processes that Katja alluded to. But just maybe a word on the name, pulsars. I mean, why do we call them neutron stars, pulsars? Well, fundamentally, when you speak of neutron stars, you're talking about their composition. They're mostly made up of neutrons. It's as if, you know, we're made up of protons, electrons, and neutrons. Most of the atoms are quote unquote empty space. If the electron and the proton come together across an entire star, suddenly you end up with a bunch of neutrons very close together. Hence the name neutron stars. They're made up of neutrons mostly. But then pulsars, that name comes from pulsating. So that's because originally there were these pulses detected back in the 1960s by this astronomer, Jocelyn Bell, an amazing woman who was doing her PhD in Cambridge, who detected the very first pulsars. And then her supervisor got the Nobel Prize. So it seemed like something was pulsing in space. Eventually, once they figured out what it actually was, they realized something was just rotating like a lighthouse. And then once in a while, it seems like you get a pulse. So there's a bit of a misnomenclature there. And Evan is thanking us. So cool. So we've addressed that one. The second question was Jay Miller, who was saying, slightly off topic, would like to hear any thoughts you have on dark energy / matter. Well, 3 minutes is not enough to do justice to this topic.
Yeah.
We'll just say that those, you know, we have a hard enough time understanding normal matter in this universe that you know, that we're made of, and that, you know, causes the sun to shine and so on. Unfortunately or fortunately, I mean, it's fun, you know, we always have new questions. That only constitutes roughly 5% of the entire matter or gravity or something in the universe. And so there's this other thing, dark matter, that Katja alluded to, and something even more bizarre, dark energy, which we really don't understand. But suffice it to say that a few years back, I mean, we know the universe is expanding. You know, the Big Bang 13-odd billion years ago created the universe as we understand it. It's been expanding, and it made sense before we went out and measured it. It made sense that that expansion was gradually slowing down. After all, there is matter. You can imagine it pulling things back towards the center, etc. Well, in the past decade plus, past 2 decades, as it turns out, using the Hubble Space Telescope and then other telescopes, people have realized, hold on, it seems the expansion rate of the universe is actually accelerating. It's as if you have some sort of anti-gravity pushing things further apart even more. And that's referred to as dark energy. And frankly, we have no clue really what it is.
Yeah. Yeah, we're also out of time. I'm actually thinking of writing a book on dark matter, specifically my next book, maybe, because there's so much to say, actually, and a lot of people who literally spent again, decades of their lives to understand what it is, and we still don't know. So that's really fascinating. But thank you so much to everybody for joining. I hope you enjoyed our discussion and maybe learned something. And yeah, it was really cool to chat again, Fernando.
Cool. Thanks, Katja. Stay well, everyone. Have a good night or day wherever you are in the world. Bye-bye.
Bye.